Have you ever seen sunlight passing through a triangular glass object and breaking into a beautiful rainbow of colors? That object is a prism, and what's happening inside it is a fascinating play of light refraction. Hello everyone, today we'll explore how a prism bends light and why it's an important optical tool in science and technology. A prism is a transparent refracting medium, usually made of glass or quartz, and it has 5 plane surfaces. 2 of these are triangular and parallel to each other, while the other 3 are rectangular. The 2 rectangular faces that meet at a sharp line form what we call the refracting surfaces. The line where these surfaces meet is the refracting edge. The angle between the 2 refracting surfaces is called the angle of prism, denoted by capital A. When we slice the prism perpendicularly to its refracting edge, we get the principal section, which is the triangular cross-section you often see in ray diagrams. As you can see in the diagram, each face and edge has a specific role to play in controlling the path of light inside the prism. Let's now trace the journey of a ray of light through the prism step by step. When a light ray, say from air, hits the first refracting surface, it enters a denser medium, glass. By the laws of refraction, it bends towards the normal, and we call this bending angle inside the prism R1. This ray then travels inside the prism until it reaches the second refracting surface. Here, it moves from glass back to air, a rarer medium, so it bends away from the normal, making an angle of emergence I2. No matter how the ray enters, one thing is constant: the refracted ray inside the prism is always bent towards the base. That's why in the diagram, the light path appears tilted towards the bottom side of the triangular section. Now comes one of the most important ideas in prism refraction, the angle of deviation, denoted by delta. It's simply the angle between the straight path the ray would have followed if there were no prism, and the path it actually takes after emerging from the prism. This total deviation happens in 2 stages, first when the ray enters the prism, and then again when it leaves. Mathematically, the formula for total deviation is delta equals open bracket I1 minus R1, close bracket, plus open bracket I2 minus R2, close bracket. From simple geometry, we know that R1 plus R2 equals capital A, which is the prism's angle. Substituting this into our deviation equation, we arrive at a more compact relation: delta equals open bracket I1 plus I2, close bracket, minus capital A. This elegant equation directly connects the angle of deviation with the angles of incidence and emergence. Let's now look at the condition for minimum deviation. As we gradually increase the angle of incidence, the deviation of the ray first decreases, then reaches a certain minimum value, and after that begins to increase again. This minimum deviation, denoted by delta minimum, occurs when the angle of incidence equals the angle of emergence, that is I1 equals I2, and at the same time the internal refractions are equal, R1 equals R2. At this position, something special happens. The refracted ray inside the prism runs exactly parallel to its base. The formula for minimum deviation is delta minimum equals 2 times I minus capital A, where A is the angle of the prism. On the graph here, you can see the I delta curve. Notice how the deviation decreases, reaches delta minimum, and then increases again. So, what controls how much a prism bends light? First is the angle of incidence. Changing it shifts the deviation, producing that characteristic curve with a minimum point. Second is the material of the prism. Higher refractive index materials, like flint glass, bend light more. Third is the angle of prism A. Sharper prisms cause more deviation. And fourth is the color or wavelength of light. Violet light deviates the most, red light the least, because refractive index varies with wavelength. This is why prisms can split white light into its spectrum. Let's solidify this with an example. We have an equilateral prism. meaning A equals 60 degrees, made of a material with refractive index mu equal to 1.5. We want to find its minimum deviation. We use the formula mu equals sine of open bracket a plus delta min over 2 close bracket divided by sine of A over 2. Substituting values, 1.5 equals sine of open bracket 60 plus delta min over 2 close bracket divided by sine 30 degrees. Sine 30 degrees is 0.5, so multiplying both sides by 0.5 gives 0.75 equals sine of open bracket 60 plus delta min over 2 close bracket. Taking the inverse sine, we get 60 plus delta min over 2 equals 48.59 degrees. Solving for delta min gives approximately 37.18 degrees. Let's quickly recap. A prism refracts light twice, bending it towards its base each time. The overall deviation depends on the incidence angle, the prisma's material, its angle, and the light's wavelength. Minimum deviation happens when incidence equals emergence and the refracted ray is parallel to the base. Violet light bends more than red due to higher refractive index, making prisms useful in spectroscopy and optical instruments. So, next time you see a rainbow through a prism, remember, it's a perfect demonstration of light's behavior under refraction. I hope you now have a clear picture of how prisms work and why they are so important in physics. See you in the next session, where we'll explore yet another exciting journey of light.